Hi there and welcome to another Expresso Mechanics tutorial. And in this one we're going to be looking at creating this, which is a piston and crankshaft setup. And we'll take a look at what we need to do in order to achieve this in just a moment. What's required is the creation of a synergy between three different components. So obviously we've got the crankshaft, we've got the crank arm, and we've got the piston head. So we're needing to create a synergy between these three objects. Let's have a quick look at what we've got in the object manager here. Each component is grouped into a null. So I've got the crank grouped into a null, the arm is grouped into a null, and so is the head. So what we've got in the crank, if we go into our end view, we can see that we've got its axis positioned at the center of rotation. So that makes perfect sense. We've also got an arm target grouped into the crankshaft, which is placed at the center of the big end bearing of the crank arm. And that's essential to make this work. Aside from that, it's quite simple in terms of the way it's set up. The arm is set up with its z-axis pointing along the actual length of the arm. Now this is important. The z-axis must be aligned along the length of the arm because we're going to be using a target tag here in order to make the piston arm point towards the piston head. So if you set it up with the y-axis along the arm, it's going to be pointing in another direction, either in the z or the x-axis, which is no good. Okay, so make sure you set that up correctly. Let's just have a look at the end view again. And what I've got is I've set this up so that we can illustrate this. Essentially what we've got, as you can see, is a right angled triangle here. So you can probably guess that we might be able to use Pythagoras Theorem in order to help us make this work. Well, under normal circumstances, of course, using standard Pythagoras, we just have lengths A, B and C, and we'd say that length A squared plus length B squared is equal to length C squared, and then we'd find the square root to find the length of the hypotenuse of the triangle. So that would be standard, but of course in this, or on this particular occasion, we know that the hypotenuse of the triangle is actually the length between the centres of the big end bearing here and the small end bearing of the crank arm. So we've already got that as a constant length. So what do we need to do? Well, we need to use an inversion of Pythagoras on this occasion. So if we just advance the timeline a little bit, you can see what's going on. So as we said, this is staying constant, but the other two lengths are changing. They're constantly changing. And the further we go, the more we can see that exaggerated here. We can see that length B here has shortened considerably, while length A has lengthened considerably. So how do we set this up? Well, what we need to do is add in the points A, B and C, and then we can have a think about how we're going to do this. What we need to do is subtract point A from point B, which will give us a length x, and it's x because it's constantly changing. What we then need to do is find the square root of C squared, so we need our crank arm's centre points there, that length we need to square that, and subtract it from x squared. So we ultimately need the square root of C squared minus x squared. So that will give us x1, a new version of x. Then all we need to do is add the arm's position y, and then that will give us the height. It will give us the height because we're going to add that basically to this length here, and it will give us the height of the piston head. That's what we've got to do. So if we just advance the timeline, we can see that the arm is now raised. So this distance is what we've got to get. And then we're going to take this constantly changing value and add it to the length AC in order to keep our piston head at the correct height at any given time between the crankshaft here and the piston head using that formula. So that's what we're about with all of this. So a little bit of a maths lesson. I hope that wasn't too boring. But anyway, let's go back to our 3D view and see how we're going to go about achieving this. Right, so the first thing that we need to do is open the Espresso Editor. We've got nothing in there, so let's start bringing a few things in. Right, the first thing that we need to drag in is the arm target. We're going to drag that in, and we're going to say get its global position because that's what we need first. So we've got our arm target, we've got its global position. Let's just view these at 100%. Moving on from here, we'll drag in the arm. And we can simply say we're going to give the arm the position. We can use the global position, but there's no real need to on this occasion as it's the parent object. So we can do that. Now let's see what happens when we rotate the crank. What we should now find is that we've got the arm following the position of the crankshaft correctly. But nothing else is working quite yet, but that's fine, that's okay. The next thing that we need to do is place a target tag on the arm. So let's get that, and we'll get that done. So we get a target tag, we put it on the arm, okay. Now our target object is going to be the piston head, because if we just go into our end view, we can see that the axis of the piston head is the target that the crank arm needs to point in the direction of in order for the small end bearing there to match up with the piston head correctly. So that's what we're about here. We know we're going to use the head, so if we say use head as the target object, and you can see that the arm instantly snapped into position and it's now in the correct place. And when we rotate the crankshaft, you'll see that the arm tries to go, well, it goes through the head. It will actually follow the position of the head. Obviously the head doesn't move yet, but you can see that the crank arm is pretty much behaving as we'd expect it to already. So the first part of this is actually very, very straightforward and not particularly complicated at all. So that's all working fine, which is fantastic. So moving on from here, the first thing we need to do is bring in the crankshaft. And I'm not going to bring in the actual crank, I'm going to bring in the shaft itself. So I'm going to bring that in. Get its global position Z, because we're going to be taking the global position Z of the crankshaft and subtracting it from the global position Z of the arm. Next thing to do then is drag the arm into the Expresso Editor. Actually thinking about it, I could have brought the crank in. Didn't have to bring the crankshaft in because the global positions of both are exactly the same, but it doesn't make any odds. Let's just bring in the arm anyway, so we'll get that in. And with this, I need to do the same thing again. I just need the global position Z. And what we then need to do is subtract them. So we'll get a subtract in there. Okay, so we've done that. Following on from here, we need a float function node, which is one that I've never used in a tutorial before. This node offers a number of mathematical functions. You've got exponents, logarithms, you've got a square root, you've got floors, ceiling, power, and of course the power of 2. And that's what we need because we want to square this, so we're going to raise to the power of 2. So that can be plumbed into here. Moving on from here, I need another float function, so I'll copy this one. I'm going to place that one there. And I also need a constant value. Now this constant value is going to be the distance between the big end and small end bearings of the crank arm. So the distance between those centres. So let's bring that constant in there. I'll put it in just for the sake of actually seeing it. I could just plumb it into this value, but I'll put it in this constant so that we can see it. And that length I happen to know is 65.5 centimetres, so we'll just key that in there. And then moving on from here, we need another math subtract, so I'm going to copy this one across and subtract those two from each other. We can then find the square root of these. So again, it's another float function, so I'll copy this one across here. But this time I'm going to set its function up to a square root, so it'll be this one. And then we can plug the output of our math subtract node into our value there on the float function. Okay. Now I'm going to go back to my arm because we also need the global position y of this. So we'll add that in now. Okay. And then we need a math add. So we'll copy the subtract, make it an add. And we can plumb in the result of our square root here and also plumb in the global position y of the arm. And that's our formula complete. That's all we need to do to complete the formula for this. And then the last part of the puzzle is to bring in the head and give it the global position y. Could just be position, but we'll say global position. It makes it easier because that means we can move the thing around and put it anywhere in the scene much more easily. So we'll put that in, just add that in there. And already we've got a bit of a problem. Now, why have we got a problem? Why have I got a problem there? I don't understand why I've got a problem. Why has that moved over there? What have I done? Have I put global position in there by any chance? Yes, I have. Okay, so I've made the classic mistake. I've put global position and I should have put global position y. And plumb that into there and take that one away. Okay. So let's get rid of that global position. Great, that's fine. Then all I've got to do is move my head. What I can do here is if I get my head, I should be able to go down here, set our Z position to 0 and our X to -30. And now the piston head is where it needs to be. So that's no problem. Rightio, so we've got that in the correct spot. And if we turn the crank, we should find that it behaves as we expect it to. And it does. It does exactly what it says on the tin. So that's doing exactly what we want it to, except that it actually isn't quite right. If we actually, what we can do, let's have a go. We've got the animation still in there. Now, if we run the animation and I just select the arm, as the crank rotates, you can see that we've got a gimbal effect in there. Now that's fine if the texture that you've got on the arm is completely symmetrical, but if it's asymmetrical, so you've got a bit of dirt on this piece here, it will be noticeable that it's changing, so that won't be any good. So how can we correct this? Well, it's actually very simple. What we need to do is get a null object and we'll name it up vector. So we've got an up vector, and what we're going to do, just going to view 2, I'm going to move this over here. I'm going to put it, it needs to be, I've got to get this accurate, so it's got to be -30. That's fine. And it doesn't really matter where it goes on the Z, but we'll, for the sake of argument, I suppose we'll just say 50. That should be fine. Let's go into our 3D view and get our arm selected again. And let's see if that's improved things. No, not quite. The reason for that is because our up vector is slightly too close. Oh no, it's not. I beg your pardon, it's not. It's because I need to put the up vector in here. So that up vector has got to be added to the target. Now, if we run our animation now, we should find it works. Let's just select the arm. Yep, and it's working perfectly now. Be careful with the placement of the up vector though, because if you place it slightly too close, if it was here, it might not do the job properly. Let's have a go with that. Let's just see what the arm's doing now. It's okay there, but if we just go and move it slightly closer, Let's see what we've got now. Yeah, now it's flipping again. So you've got to be very careful with that placement. So if you do get a problem with flipping, even when you put an up vector in, just get a hold of it and move it further away from the crankshaft. Just provided it's in exactly the same plane along the x-axis. That's the important thing. It must be at -30 where your arm and the arm target are. They're all at -30. So it must match. Everything's got to match, actually. Those centres are important. If you get it even slightly wrong, the thing will work for a while and then it will gradually tear itself to pieces. So you don't want to do that. You've got to make sure it all matches up. Okay. So that is essentially the tutorial. We've learned how to create a synergic reaction between a crankshaft, a crank arm, and a piston head and get it all working beautifully just by using an inversion of Pythagoras. Not as horrifying as it perhaps sounds. I mean, at first, I think it looks really, well, you think it's going to be really complicated. I mean, in fact, there is a more complex way you can do it using trigonometry. If you're a real mathematical genius, you can actually do it. But that's a much bigger expression, actually. I have seen it done, but I don't fully understand how it works because I'm not Mr. Mathematician, but you can certainly do it that way. But anyway, that's your tutorial. I hope you've enjoyed this one, and I very much look forward to seeing you on the next one. And I suppose as I'm now on YouTube, I must utter the immortal words. Please subscribe to the channel, and if you like the video, please give it a thumbs up. See you soon. Bye for now.